Good evening, all. Welcome to the live session for optimization from fundamentals course. We are in week 11. We have one more session, and I'm planning to have one more extra session as well. It's like after the week 12, we'll have one more extra session just to kind of summarize over all the topics. You will receive a mail regarding that as well a little later. But that wouldn't be on a Saturday. I'm planning to have it on next Sunday probably, not this Sunday, the coming Sunday after week 12. So the coming Sunday, as in 13th of April. Now coming to this week, so today we'll be discussing on the last week we ended our session on penalty methods. We understood that penalty methods are used to kind of convert a constraint optimization problem into an unconstrained problem, and then you can use the existing techniques for unconstrained problem to solve these problems. Now we will discuss the two different kinds of penalties, L1 and L2 penalties, and then we will understand what are the limitations of these methods, and then we'll go to augmented Lagrange method. Once we complete both of these are in general, these are for nonlinear problems. Then we come across something called cutting plane method, which is a way to convert a nonlinear problem into a linear problem. And then finally, we will see something called interior point method. And with that, we'll go on to some problems and some theoretical and some numerical problems on these particular concepts. The first one is the concept of penalty, which we discussed even in the last week. So the aim is to convert a constraint to an unconstrained problem. So when we are doing that, what we are trying to do, the first case is a quadratic penalty term, that is say L2. So you want to minimize a function f of x subject to the constraint. So the problem is minimize f of x where h of x equals to 0. Let's say we have only the equality constraint. So for this kind of problem, we discussed last week that a penalty function that you can impose something like f of x plus some ck times norm h of x whole square. Since we are using whole square here, we are calling this a quadratic penalty or L2 penalty. Now, what we try to do is we keep increasing the values of ck, start from some values as 0 or something, and then you keep increasing the values of ck. So what will happen is when you try to use some optimizer to minimize this overall function, it will eventually come to a point where the h of x will go to 0 and the minimum will be equal to the minimum of whatever f of x is. So that will you recover the original problem by gradually increasing ck. So if we do it, say for example, if this particular function is differentiable, then so we are not explicitly keeping the extra condition saying that this h of x equal to 0. If you remember when we did, for example, say the Lagrangian method, so we defined Lagrange as something as L of x comma lambda, or let's put theta as something like f of x plus theta times h of x, something like this. We defined as the Lagrange, and then we did the gradient of L should to be equal to 0 with respect to x, and then we also put an extra constraint saying h of x equal to 0. Both of these have to be satisfied. Only when you solve both of them, you will get the corresponding x star and theta star, and these are my Lagrange multipliers, and this is the optimal solution that I want. So somehow we are always keeping this extra constraint. So we are not solving as if it is an unconstrained problem. But now what we are trying to do is we are trying to solve it as an unconstrained problem. So we have only one equation, that is only this we have to minimize. We are not saying that this extra condition is not explicitly specified. So we want that to happen automatically. So what we are saying that in an indirect way is when this ck tends to infinity, the only way this entire function gets minimized is make this h of x equal to 0. If this turns out to be 0, because there is a huge penalty for it for any small, even a small value, small positive or positive value of this particular term, that will not be a minimum. So that's the whole idea. So you don't have to specify this explicitly. So if you take a derivative, so now which means this is an unconstrained problem. So here for this particular case, x belongs to Rn. Once we say x belongs to Rn, then we can use our necessary and sufficient conditions that we have discussed long before. All you have to do is the necessary condition is the gradient of this particular function should be equal to 0. So if you take the gradient of this, so that would be del fx plus tk times 2 times hx times del hx equals to 0. So for example, if x star is the optimal solution, then we already know that let's say if x star is optimal and del f is also 0. Let's assume that it is 0. Then this particular term here should be 0, which could happen in two different scenarios. Either you have h of x equal to 0 or del h of x equal to 0. Either of them will lead to the center equation to be true. But let's say if for example x star is h of x is not equal to 0, like out of this one of them can be 0, the first scenario is if x star is infeasible, which means x star is not satisfying this particular equation, h of x equal to 0. Then what would happen is this is not 0, but then del hx can be 0 and still this entire equation will turn out to be 0. So which means when you try to solve this particular case, you can end up in a scenario without actually just minimizing this is not always sufficient, because if you use some gradient based method, you can end up in certain points where del fx is 0 and at the same time del hx is 0, so that is called a stationary point. If gradient of a particular function is 0 at a point, you call that point a stationary point. So at the stationary point, this will be 0. And if it so happens for that function there del fx was also 0, then you do not have h of x equal to 0. Then the solution becomes infeasible. So this you can also end up in scenarios like this. However, if for example x star is feasible, then we know h of x is 0. So this term will be 0 and del fx is 0. So that is anyways a minimum. That is something that we already know about. So then it means that we are again solving the KKT conditions. So just to put the same thing again here. So what we are trying to say now is this term over here. So if you take the Lagrange and derivative of Lagrange, so del x, this is my Lagrange. Del x of Lagrange, derivative of Lagrange is del f plus theta times del h. So if you compare this equation with the equation over here, you can see that this theta is equivalent to this particular term. So like both the methods, if you compare both these things, all we are trying to do is we know that once we solve using Lagrange method, like if it satisfies the KKT conditions, then that particular x star is an optimal solution. That is something that we already know from before. So if you take that fact, then theta is some particular constant. We know the condition that we kept is theta has to be greater than or equal to 0. This is the constant we kept on that. So this ck times hk should be equal to theta as this tends to infinite. So once we keep that constant, what happens is we get that h of x is theta by ck, and we need h of x to be 0 because that's what the original problem is. Whatever x you find, for it to be feasible, h of x have to be 0. So if this has to be 0, then either you have to have theta equal to 0, which means that particular constant is not active anymore, but that may not always happen. That is only a kind of a special case. So the other option is to make this ck tends to infinity. So which means we need to have a very high value of C to actually get a solution of x star, reasonably accurate solution of x star, which is not always possible. So the other way to go about this is called an L1 penalty. So instead of keeping something like hx whole square, what we are doing here is just take the absolute value of it. Even here the problem is the same. If h of x is greater than 0, then you will have some finite positive term here. If it is less than 0, it will have a finite positive term here. Only when it is exactly equal to 0 is when this term will vanish, and minimizing f of x is equivalent to minimizing q of x. So the basic idea of penalty is true here. So whenever the x lies inside the feasible region, this penalty will be 0. Whenever it lies outside the feasible region, the penalty will have some finite positive value. That's how we define the penalty for a minimizing function. So this is also a valid penalty function. But the only difference here is this particular function is not differentiable. So we cannot directly use a technique like this. But if you try to compare this with the Lagrange, you can see that this particular term ck will directly map it. So if the Lagrange will go as f of x plus some theta times theta j times h of x. So you can see that depending on the ck is somehow related to this theta j. And just to keep in just to ensure one more thing. So whenever we have a penalty function, for example, let's say ck equal to 100, gave me an optimal value of f star, say around 1000 or something. If ck equals to 1000, then the optimal value I am going to get here, let's put some number here, let's say this is c1 and this is c2, then f2 star, whatever it is definitely going to be less than or equal to f1 star. Like as you keep increasing the penalty, then the chances of getting this entire this is q1 star and this is q2 star. As you keep increasing the value of penalty, then the chances that this particular thing will go to 0 will increase, and then f will also, the more accurate, the more closer to the actual solution you will be. So as you keep, like for example, if this particular thing is sufficiently accurate for you, you don't need the other decimal places here. So you have some decimal places here, some values, but then these might not matter to you in your particular case. like you might not require that high precision. So you can stop at this particular value of C and terminate your problem instead of keep on increasing the problem. Like as you keep increasing the C, this precision only is going to increase. So you will eventually stop at a point where you are sufficient with whatever precision you have. So in L2, what we know is we need CK to be very high in order to get even this close to 0. So for example, if you need h of x to be less than say 10 power minus 3 or something, like this is the amount of tolerance you want. For example, if you're having the CFT equations, you have a continuity equation that has to be that has to be always satisfied, but you cannot always make it to exactly 0. You have to put some tolerance on it. So depending on that tolerance, you will have instead of being infinity, this will be some finite value. That finite value is something that you have to keep trying. You have to start with some C and you have to keep increasing till you reach that particular finite value beyond which this particular tolerance is satisfied. That maximum C value is something that is very high in case of an L2 penalty compared to what we get in an L1 penalty. The reason for that is if you have gone through the lecture videos, I think it would have been stated there as well. So L1 penalty is something like absolute value where L2 is a quadratic clause. So up to a certain point, so if this is this tolerance, whatever, let's say this is my tolerance, or say this is my h of x value, absolute h of x value, and this is the penalty term that I'm considering. So this is my penalty function. So if I plot this, you can see like whenever the value of this epsilon, the tolerance is less than 1, then in that particular scenario, the penalty is much higher for L1. This is my L1, and this is for L2. So since you are having a higher penalty for L1 automatically natively incorporated into this particular coefficient here need not be that high to actually get the same amount of precision you reach. So in that way, L1 is kind of good only when you have this tolerance is when you are in this particular region. The moment you are in the other region, then L2 becomes dominant. So when you are far off from your domain, like when you are far off from your solution, then using L1 might not always is not optimal. Again, the problem here is even here the value of C, again, it is lower than L2 penalty, but it may not always be too low for you for it to be some of practical use. So then the next technique is something called augmented Lagrange method. The idea here is we use the Lagrange concept. So we take the normal Lagrange f of x plus this term, plus we also have the penalty term, the L2 penalty term here. The advantage, what we try to do is if we just couple these terms together, so we have a theta common here plus C times HA. So what we try to do is we try to estimate the CK such a way that this entire thing will approximate my original Lagrange multiplier theta j star. So then I can always equate this to theta j star. So if you just rearrange the equation, so you can have HA to be equal to this. So all I have to do is find this particular theta k such that theta k will be equal to theta j star, then h of x will be equal to 0. And without even actually trying to get the CK equal to infinite. Like previously, if you recall, this is just theta j by CK, something like this when I just used L2 penalty. If I just use this term, then it is just h equal to this particular term, and then I have only CK tending to infinity. Only then I can find an actual solution. But now, instead of all of that, all I have to do is start with some theta, and then what I do is I keep for that particular theta, I will solve the problem, get an x value, and for that x value, I will see what this particular constraint is satisfied or not. For example, if you have continuity equation, you have some velocity field, you start with the velocity field, substitute that velocity field, get the continuity into the continuity equation, and that will give you how much error you have. Now what you do, you update your theta value so that this continuity you update the theta value and then again solve this equation again get a new x, and you keep doing this. So eventually what will happen is this continuity equation will eventually be satisfied and this term will be equal to 0. So how will you identify that is you monitor this particular term theta jk plus 1 minus theta jk. If you monitor this particular term with respect to, like, if you just normalize it, this is the residual, and this will eventually kind of settle to some small value. Once this becomes close to 0 or whatever tolerance you set, say 10 power minus 6, 10 power minus 7, then you will stop iterating, and that is when your h of x would have converged. It's like if both of these are equal, then h of x is 0. I don't even have to have a very high value of ck for this to be 0. All I have to ensure is this will only determine how fast or slow that residual is kind of converging to 0. So if I plot this versus my iterations, I'll just put k here. Initially it might be high, but gradually it will go to 0. And I'll stop at some point. So this is some value, say 10 power minus 6, 5 or 4, whatever that value, depending on the problem, and then that's where you stop iterating, and then you'll get the value of h of x. And that is the x that which will be the solution of your original problem. The most important point here is here we are doing we are solving for two things. So this update will like once you keep doing these iterations, you are eventually reaching a theta j star. So we are finding theta j, which is a Lagrange parameter, Lagrange multiplier, and at the same time we are also solving for this particular problem. Like we are at every iteration we are solving this equation. In this equation we are getting xk. So we are solving for x also. So we are solving both for x. X is a primary variable and theta is a dual variable. So this is kind of a joint optimization. It solves in both primary and dual at the same time. So the same idea here. The main point I would like to take home from this is if, for example, you find a particular C where this particular condition is satisfied, then you can always use a C that is greater than the threshold and still get the same solution. So which is same like you, for example, if I keep a penalty of 100 and I got a solution, then if I keep a penalty of 1000, then also I would get the same solution. But if I keep a penalty lower than the threshold, then I might not actually reach that particular solution that fast as I have reached before. So as I said, like this parameter penalty will only decide how fast or slow this converges, and that also depends on the problem. This is a kind of trial and error. You have to start with some small value, keep increasing it, and beyond a particular point, you will eventually reach a solution. And once you reach that, any value of C above that is going to give you the answer. Yeah, I hope it is clear until now. Next one is the concept of cutting plane. So whenever we have a nonlinear problem, so we can always convert it into linear problem. So by something called constraint linearization, we will solve an example problem on this. But to just give you a rough idea, so you have this we have done even before. That you have okay, maybe I should give some convex there. Let's say this is my feasible domain, yes. I can always approximate it with a convex hull, which we have done even before. So I can do something like this. And use this convex hull. Like once I have this convex hull, then it becomes a linear problem, which we have already know. Like it becomes a polyhedron kind of thing. And once it is a polyhedron, we know how to find the solution. We know that optimal will only be in one of these points. So the problem gets simplified a little, but the only challenge now is whatever optimal you get, it may or may not lie inside the feasible region. So the idea here is first you take a nonlinear constraint and then you linearize it with some hyperplanes. How do I choose the hyperplanes? How many lines to consider? And all of that is something that we have to choose depending on problem. But let's say you kind of split it into some set of hyperplanes. Once that is done, even the objective can also be linearized. So you can linearize it by adding one more extra constraint like this. Once it becomes an LP problem, you can solve it normally as we would have by any of the methods. Like there are so many LP methods outside, say simplex or something. You can use that method and solve the LP problem and get a solution for it. And once you get the solution, you will check whether that particular solution lies inside this feasible region or not. If it is lying inside the feasible region, then we have already solved the problem. But if it is not lying inside the feasible region, then we can use the separating hyperplane theorem, which we have done before. Like this is true only when you have a convex set. So you have to have S should be a convex set. Hello. Is there any question? Okay. So if you know that S is a convex set and this particular point is not lying lying outside the convex set, then we always know that if this is some convex set and you have a point that is lying outside the convex set, then we can always draw a separating hyperplane between them. That is something that we have discussed before. So once you draw the separating hyperplane, then that will be my, for example, if this is a point, then I can draw a separating hyperplane here, and that will give me the new polyhedron. Once I have that new polyhedron, again I will have the new points, and again I can solve the LP problem. And again I'll keep doing this till I reach a point where that is feasible, like till I reach an optimal point of the LP problem, which lies inside the feasible region. And how do I move from this point to this point? So for example, if GI is a constraint, you want that to be 0 or less than or equal to 0, but then if it is positive, then all we have to do is move in a direction that will reduce this particular value. So all we have to do is take the current value and take the gradient of it. If I move along the gradient direction, the value is going to increase. So I'm going to move away from it. So the new direction, this is just a linear approximation. If I take a linear approximation at the new point, x minus xk, or this is just to show that you are moving in the opposite direction to the gradient, such that you take the value of x such that this entire thing is less than or equal to 0, because we have to move into the feasible region. This is clear? Maybe it is clear. Yeah. In this particular set, it's like you have, if you take 2 points and you approximate with this thing, if this particular value at this intermediate point, whatever you have taken alpha value, if it is greater than this, then it is a convex set. It is a convex function. Concave is exact opposite of it. If you just invert it, then it will be concave. Or to put, if you want to understand it in another way, it's like if you take any linear combination of them, that is going to give you a very high value than the original function value. The last one is an interior point method. So here what we try to do is again is try to solve the same LP problem. So that is, say, minimize T transpose X such that Ax equal to P and x greater than equal to 0. And you also solve the dual problem at the same time. So that is maximize P transpose Y such that you have A transpose lambda greater than or equal to C, or I'll just put equal to C, and you have S greater than or equal to 0. You solve both of them together. So the idea is to essentially find an X and S that will satisfy both of these. So the main problem is to, like, the set of constraints that we have, identifying whether the point lies inside the particular set is or not is the main problem here. So what we do is we take these both equations together. So one equation is Ax minus B equal to 0. The other equation is A transpose lambda plus S minus C equal to 0. And then we also have the extra constraint that the complementary slackness condition. So if X is some finite value, then S should be 0 and other thing. So that is the next constraint that we have, X times S equal to 0. So you can see that this particular thing is essentially just the summation over all the variables you have, sigma X I S. How many decision variables you have, that many variables. Like we know that both an X and S have to be positive. So if the product of this is like when you have take summation of some n positive numbers and put that equal to 0, then each one of them have to be 0. There is no other option. So if you solve this, now all we have to do is find a particular value of X lambda S such that this particular F will be equal to 0. How do we solve that? We use the Newton-Raphson method, which we have already discussed before. So all you have to do is J times delta equal to minus F prime. So what is this F prime? So ideally you have to just put F here, but then the problem that would be coming is if you directly put F here, all it will try to do is make this X lambda S, or like it will find some X lambda S, but then there is no guarantee that it is going to satisfy this constraint. So in order to satisfy this constraint, you have to enforce that somehow. So you'll either make X0 or S0 one of them, which would cause some problems. So just to kind of circumvent that, we add some extra term here. This is kind of, it is again, nothing is going to change here. Once you reach your solution, this particular term will anyway go to 0. Like you need to have sigma xi equal to 0. So once that is equal to 0, this particular term will be equal to 0. So this entire term will just go to 0. This is just like you're going from some point to another point in different ways. So one way, let's say you're going something like this. The other way is a kind of like you know that you are kind of oscillating. Since you know you're oscillating, instead of taking the update directly, you just go in some predetermined direction. it is just like since we know that we are going to oscillate around, we are just subtracting that term over here, and then we are kind of going in a straight way so that you will reach much faster. Otherwise, there is nothing over here. So, but how do I decide how much to take? That is something, this constraint is still there. So whatever delta that I am moving, I have to always ensure that this particular both the x and s values are positive. And to do that, I have to vary this particular alpha. Like the update equation still remains the same. The original Newton-Raphson update just tells you have to do just put this delta. But now comes the extra term alpha that you have to choose at each and every step so that your x and s are always positive. It's like how do you do that? Like if you want to put it algorithmically, you have to start with some alpha, get the new value of x and s, see if they are positive or not. If not, you either depending on the sign of them, you either increase or decrease the value of alpha, and you keep doing it till the values of x and alpha are positive. This is something similar we did even in the line search method last week. Is this clear till here? I think it is clear. Yeah, this is matrix. Okay, then we will solve some problems. Maybe you can answer them. You want to minimize some function f of x such that h of x equal to 0, and we want to solve it using L1 penalty method. Which of the following statements is false? We will say one by one. So will the algorithm converge to local minima with a finite value of the penalty method? True or false? So if I want to use a penalty method, so my new objective function will be something like q of x comma c equal to f of x, and I'm saying use L1 penalty, so that will be c times modulus of h of x. So this is my penalty function. So the first option says the algorithm converges to a local minima with a finite value of the penalty method, which means that c is finite. With a finite value of c, I can reach an optimal value of f. Is it true or false? Okay, why? That is for an L2 penalty method. When you have f of x plus c times h of x square, then if you compare this with your Lagrange, so this will be f of x plus c times h of x times h of x. So this will be my Lagrange parameter, right? Then you say that theta equal to c times h of x and h of x equal to theta by c. So h of x will be 0 only when c tends to infinite. But if you compare this with my Lagrange method, f plus theta times h of x, so if I choose an x such that h of x is positive, then c will be equal to theta, and theta is some finite value. Then true. Okay. What about the second one? The objective of the penalized problem is differentiable. Is this differentiable? Okay. So what would be the differential value if I want to calculate? Say it's only one function. It's a del q del x. What is del q del x? Plus c times. No, this is an absolute symbol here. There is a modulus here. No. Derivative of modulus is something like x by h of x times h prime of x. So if you just draw the modulus function, this is my x and this is my mod x. So mod x will be something like this, right? So what is the derivative at x equal to 0? As x tends to, if x is positive, then the derivative is plus 1. If x is negative, the derivative is minus 1, right? So it is not a differentiable function. Mod x is not differentiable at x equal to 0. It has a discontinuity here. Like it is a continuous function, but then it is not differentiable because of this modulus. And this is exactly the reason that even if you use an L1 penalty, you cannot directly use the gradient based method. that like you can use, but it would be a little difficult, tricky to kind of take this into account. So you have to use some methods which do not use gradients. The last option, L1 penalty penalizes less severely than the quadratic penalty for points which are far away from the feasibility. True or false? True. Okay. Why? And what about L1? No, but L1 also goes to infinite, right? So if I plot L1 and L2, so what this question asks you is how does it penalize the value? Like when I take this q of x, this versus this. So when I take mod h of x, it will be something like this. It will be a linear function. And h of x square will be something like a quadratic function like this. So what happens is when you are, and if you are close to this particular point 0, like we want h of x to be 0. So whenever you are close to 0, then you are close to your feasible solution. When you go away from 0, you are moving away from your feasibility, right? Now what we are saying is as you go away from, far away from the feasibility, as you are going far away from the feasibility, which one is higher? This is higher, right? If you are far away from the feasibility, only up until 1, like 0 to 1 is when mod x is greater than x square. But once you are above 1, then x square will always be greater than mod x. So when you are far away from the feasibility, L2 is going to penalize you much higher than L1. Yeah. So this is true. So L1 penalty is less severe than quadratic for points which are far away. But as you come closer to the feasible point, as you come closer to the feasible region, then reverse of the statement is true. So here it asked about the false. So second option is what you should be choosing. Okay. The next question. Consider you have an augmented Lagrangian method for minimize f of x such that h of x equal to 0 for all these k values, and lambda be the Lagrange multiplier with c greater than 0 be the penalty parameter. Which of the following is false? So first tell me what is the augmented Lagrange function for this? So augmented Lagrange will be a function of x, lambda, and c. So what will be that function look like? It should have objective function for sure. We'll have f of x. It should have the constraints, that is my Lagrange multipliers. So sigma lambda j times h of x, and it should also have the penalty terms, that is c times sigma h of x whole square. This is how my augmented Lagrange function looks like. Now what we are asking is first part, which of the following statements are false. So the first is, for updating the value of xk, we need to solve an optimization problem. So how will I find the value for, so if I put k here, so I will start with some xk. At some particular iterate value xk. Okay, let's put on the superscript. The subscript is for this xk, lambda k, and ck is where I will start. Then I'll have that particular function f of xk plus sigma h of xk plus my penalty terms. Right? Now I have, what I have to do is first find xk. So how do I do that? Is I have to just do the derivative with respect to x and then equate it to 0. From this I have to find xk. So this itself is an optimization problem. So first I have to find an xk, and then I have to find lambda k. So from this I'll solve and then I'll get an xk. Like I'll start from some xk and then I'll get xk plus 1. So first I have to solve an optimization. So this itself is an optimization problem. I have to minimize this. And at each step, we update the dual variables lambda j. So once I do this, all I have to do is next down I have to update my lambda k. So I'll update my lambda j k plus 1 as lambda j k plus I'll take the current value of ck times whatever that particular equation I have at that particular xk. From this xk, I'll calculate how much deviation I have from the constraint, and that constraint will give me the new value of lambda. And once I get the new value of lambda, I'll again substitute in the first equation, update my xk plus 1. And again, I use that xk plus 1 here and keep, this is something that keeps happening. So it's not a single step process. You have to keep doing it. Like you have to keep iterating it. How long will you iterate? You will iterate till the lambda value does not keep changing, like below, or the change in the lambda value is within certain tolerance, whatever you have pre-decided. So the second part is at each step you update the value of dual variables, that is this particular step. So this is also true. If f is convex and hj are linear functions, so if this is convex and these are some linear functions, the linear functions are also convex functions, then the augmented Lagrange may not be convex. But you know, the penalty that we are adding here itself is a convex function. Like it's just a quadratic function. So this is convex. When you add three convex functions, it's going to be convex. It's like it will always be convex. So this is wrong. It is not necessary to take c tends to infinity in order to solve the original constraint problem. So this is the main advantage of augmented Lagrange method that we have started out with. So the once you define like this, you can have a finite value of c, and once your lambda becomes equal to your Lagrange multiplier, then that problem will actually be solved directly. So you don't need to have ck tends to infinity, and that is what this statement is saying. So this is also true. So the only statement that is false is this particular one, that this, if the functions are if f is convex and hj is linear functions, because the penalty is also quadratic function, the entire augmented Lagrange will also be a convex function. This is clear? Yeah, the next one is again a simple theoretical problem. So we discussed the cutting plane method. So does it have an algorithm to solve a linear programming problem? Okay, so what? So when we discussed cutting plane method, so you have a nonlinear problem, yes, and from S you are converting it to some set of hyperplanes P, and then you are solving something. This is the LP problem. You are trying to solve something, and then you get a solution and check if that lies in S or not. If it lies, then you stop. Otherwise, you keep doing this. So what cutting plane method tells you is only this thing: how to get this P, and one how to update this P depending on if X star lies in S or not. You'll keep updating the P, right? So the solver that we are using inside the LP problem is something else. This solver is not a cutting plane method. This is some other solver that we have to use. We have not discussed what solvers we are using for linear programming problem in this particular course. If you're interested, you can look up something called simplex. It's an algorithm that is used to solve LP problems. So what cutting plane method tells you is you have how to kind of formulate your constraints. It will only tell you how to say if it's kind of in your CFT. If you want to understand in terms of CFT, it's just a way to kind of meshing. All it tells you is how to mesh the given geometry. You start with a mesh, and cutting plane method tells you how to refine the mesh so that your results will get better. But the actual solver is something else. It will only give you the mesh. This P is basically the mesh that you got. Then you have to use some solver, say simple. If you are familiar with CFT methods, this solver is something like a simple or PISO or some algorithm that you use, solve it, get the new solution, and then you see and refine your mesh or something. So how to do that? This second part is where the cutting plane method comes. So it doesn't give an algorithm to solve the LP problem. That's clear? Okay. So which of the following optimization problems cutting plane method may perform poorly? So what are the assumptions that we have used in the cutting plane method? The main assumption is you have Like the whole idea is you start with some discretization and then you need to find a solution, and if the solution is not lying in that particular whatever feasible original feasible set is, then you have to somehow refine your original discretization. So this refinement we have used hyperplane separating hyperplane theorem, and that requires us that original domain itself is convex. This we have discussed some time back. So only when you have a convex set, let's say this is a convex set, and if some particular point is lying outside it, then I can draw a separating hyperplane from the point and this thing. For example, if you have a concave, not a convex set, it can be something like this. Then if this is a point that is lying outside the set, then there is no guarantee that I'll draw some plane like this, but there is no guarantee that this is going to separate both the point and the space. So this plane can actually go inside. So only for convex sets we can be sure. Like you can also even in this scenario you can end up having a point here and then you draw a separating hyperplane and then it might work. But that is just a coincidence kind of thing. It will not happen. It is not guaranteed that you always end up like that. Only when you have a convex set is when you can be sure that you can have a separating hyperplane, and then you can use that to kind of make an outer approximation or make a convex hull of whatever domain you have. So it works for convex problems. Quadratic is again a convex, so this will also work. But anyway, the idea is on the constraints. It has nothing to do with the objective function, so this has no relevance whatsoever. The linear objective function over non-convex sets. So the problem here is with the non-convex set. The moment you have non-convex set, you, depending on your choice of initial guess and how you proceed, if you're somewhere here, you might get lucky, but if you end up here, then you are kind of doomed. This particular technique is not useful. So this is the main point. Yeah. So this is on the interior point method. Maybe you can answer it. Which of the following is true for interior point method? So it is a primal dual method, true or false? Okay. At each step, a linear system of equations is to be solved. So where exactly are we solving linear system of equations? So we are trying to solve this particular function. So I think this is what you are referring to. We are trying to solve this particular equation subjected to these particular constraints. Uh, this is a linear problem. Ax equal to b is a linear problem. This is also linear, but here you have a product of two terms. Here is where the nonlinearity comes. So if you take this equation without this particular term, then I just have these two things. So this is just a linear equation. I can solve it directly. But then the moment I have this x times s, this becomes nonlinear. But again, if you were saying like eventually, and that is the reason I'm using Newton's method, because it is a nonlinear equation. We are using Newton's method. Now in the Newton's method, again I have to solve this particular equation, which is linear. So I think this is what you are referring to. So this is again linear. So for each iteration, again, we have to solve this linear equation, but the original equation that we are trying to solve is not linear. That is a nonlinear equation. So this is a primal dual method. So I think this is that j times delta equal to minus f step. The algorithm checks at extreme points for optimality at each step. So are we checking anything like that? Not in this method. We are not doing any check like that. So instead, we are directly moving in some different way. We are keeping something like this. We are using this extra term, and we can vary the sigma depending on which, like, so if these are the extreme points, we are not actually moving to the extreme points, checking all the extreme points before reaching the solution. We are directly skipping all this and directly going to the final solution. So I mean that exactly is the name in it. The name says it's an interior point. You do not go to extreme points. You go through the domain to the final solution. So this is false. This is the kind of true if you consider this, but the way that I intended this question is to say that f is actually non-linear. So I'm not keeping this one. I hope that is clear. Okay. Which of the following cases you do not need to solve an optimization problem explicitly in each step of the algorithm? So it's like the whole problem is optimization, but even inside substeps, you do not have to solve a separate optimization problem. So in penalty method, are we solving one optimization or multiple optimization problems? Each time you start with some c1, you get a solution, and then you go to c2 and then get a solution. You keep doing this. For each value of c, you have to solve the optimization problem. Yeah, so this I have to solve. What about augmented Lagrange method? So am I iterating something there? This penalty method. In penalty method, we are updating ck. So I'll just put just write ck here. Ck is something that we are updating. In augmented Lagrange method, ck is fixed, but we are changing something else, right? So if you this is something in the augmented Lagrange method. So you have some f of x plus lambda times h of x plus c times h of x square, and we are kind of updating lambda at the next step to be lambda k plus whatever ck you have times h of xk. And once I get this particular lambda k plus 1, I have to substitute in the original equation, and from this I have to get my xk again. So from this I'll use lambda k plus 1 into this one and put del L equal to 0. From this I'll substitute with respect to x equal to 0, and from there I'll get my value of x and use that x here. So at every step I'll choose a lambda because I do not know the lambda value before. I have to start with some lambda, solve this optimization problem, get a value of x, again use that x, get a new value of lambda, again solve an optimization problem. So here also I'm kind of iterating, just like in penalty method we are doing with ck. So all we did is convert the problem to it. So instead of varying ck, we are fixing the ck value now and varying the lambda. That's the only difference. But then still we are solving the same thing again and again. So it's like you have an inner optimization. So what about cutting plane method? So again, the same thing. So not like that in the sense. Okay, if you, I think you're saying something like this. So this is my original domain. So in the domain, I'm kind of somehow discretizing it first. For each discretization, I have to solve an LP problem, get a solution, and check whether that solution is lying in that or not. So what am I doing in cutting plane? I have my S. This is my original domain from which I'm getting my PK at some iteration PK. Once I get PK, I'll use some solver to get an X star and check if this X star is in S. If it is in S, if it belongs to S, then you stop. If it doesn't belong to S, then what you do is you update your discretization. It's like you refine your mesh or do something like that. Once you refine the mesh, again you solve, you get a new value of X and you keep doing it. So this solver is the original optimization problem that we are running, that the LP problem. So here also we are kind of doing the same thing again and again. So we need an optimization solver again. Like there is an original optimization problem, but in addition, because of this iteration that we are doing here, because the original domain is kind of approximated in this way, and we do not know before that whether this approximation is correct or not, we have to iterate again and again. The same thing happens in all the methods. This is common in all the methods. In the penalty method, we do not know what is the correct value of C beforehand itself. So that's why we have to keep iterating to find the actual value of C also. In augmented Lagrange method, we do not know the value of lambda. So we have to keep iterating to find the value of lambda in addition to, so essentially we are solving for two variables now. The original optimization problem is for solving x, but in addition to x, here we are learning C, here we are learning lambda, here we are learning the pk. What is the correct pk that is kind of enough to give you the answer. So the moment you have an extra variable, then you are solving two optimization problems. So what about the interior point method? How many variables are we solving for that? No, interior point method will prevent that. So it will try, it knows that you are anyway going to end up in a sine wave. So it will try to avoid that sine wave completely. Or if you understand the logic that I told you before, like in penalty method, we do not know the C value before, right? That's why we are solving two times. The same thing in augmented Lagrange method. We are in all of these problems, we are solving for C and X. Here we are solving for lambda and X. Here we are solving for pk and x. And how we are solving it is first we solve the first problem, use that solution, and then put it in the second problem, get the new value of lambda, put it in the first. That is what we are doing. So we have two problems. We have the original problem one, problem two. We solve the, you take the, say for example, lambda from problem two, use that in problem one, and then get the x value here. This is what we are doing always. So this gives us like you have to solve this, like multiple iterations you have to do. But then in interior point method, what we are doing is we are solving both x and lambda together at the same time. That is how we formulated the f value here. The f that we have here is has both x and lambda in the same equation, and we are solving for f directly. So that is how we kind of overcome this entire thing. So we don't have to solve one, get a solution, go to the next one. We don't have to do this here and there. Instead, we directly go to the solution by solving both of them simultaneously. Okay. So this is something completely avoided in interior point method. And that is the only method where you solve for only one optimization problem in the joint space of primal and dual. Previously, I told that even augmented Lagrange method is solving in the joint space of primal and dual, but then it is kind of switching from one to other. That will increase the number of, it give you something like this, the sequential nature. So you have to solve one optimization followed by subsequent, and that loop keeps on going. But in interior, we kind of skipped it altogether. So that is because if you have a domain something like this, if normally if you use any of these augmented Lagrange or anything, you will keep moving from one point to the other point. So if, for example, this is my optimal solution, but somehow I started here. So then from here I have to move here, here. I have to go across all the points, only the boundary points, because that's what we discussed before. For an LP problem, your solution is going to only lie at the extreme points, right? Basic physical solutions and all of that. So you keep moving on the boundary. Here there are only 5, so it is not a big deal. But when you have a very complicated boundary, you can have so many boundary points. Instead of going through all of them, in the interior point method, what we are doing is we can directly go like this. So we are not going through the boundary, but we are going through the interior of the domain. Okay. And this is achieved because we are solving in the dual space, like both the primal and dual together, not separately. Some numerical problem. Consider this particular problem. It determines the factor penalty factor with L2 penalty. So you have to minimize the function f of x equal to half x1 square plus x2 square, and the constraint is x1 equal to 1. You can directly see and tell me the solution. You can put x1 equal to 1 here, and the minimum occurs when x2 equal to 0. That is straightforward. But then if you want to solve it, what is the penalty factor that I have to use? So what is my penalty function? What is my q of x comma c? I said it is an L2 penalty. So what will it be? F of x plus so what is my new objective function with an L2 penalty? I have to have C times whatever is my constraint, and since I am saying L2 should be square, right? The question I've asked you is to find this value of C at which I'll get an optimal value. How do I solve this? So now we know that once I put this in this form, and I can write minimize Q such that both my x1 and x2 belongs to R and R, both are real numbers. Now it becomes an unconstrained problem. The moment I put penalty function, it becomes an unconstrained problem. And my C is greater than 0. So this is my problem. So how do I do it? Since it is an unconstrained problem, I can directly take del Q by del x1 equal to 0. This will give me x1 plus equal to 0. What is the value of x1 here? Similarly, I can take del Q del x2 equal to 0. Will give me x2 equal to x2 star is 0. What is the value of x1 star? Something like this. Now we know that this is an L2 penalty, so the value of x1 star will depend on the value of C. Now depending on the value of C you choose, the value of x1 star is going to change. That is for sure. So if you choose C equal to 1, you'll get some value. If I choose C equal to 0, I'll get my x1 star equal to 0. I should put something like this. C and x1 star. If I substitute C equal to 0, I get this equals to 0. If I put C equal to 1, I get 2 by 3, and so on. So what will be the value of x1 star when I put C equal to infinite? So this is where I was telling, like, you have to fix on a certain amount of precision for your variable. So once I say that I'm okay with x1 not changing beyond a certain value of, say, as long as, so this is my k, I put k here, 1, 2, and so on. So C1 is 0, then I have x1 star equal to 0. As C tends to infinite, I'll just put C tends to infinite. My x1 star is going to be this term goes to 0 and this will be equal to 1. So as C tends to infinite, this x1 star goes to 1. But I do not have to actually go till infinite. For example, say, let's say C equal to 100 or something. Then x1 star will be 2 by, you can just put, yeah, 2 by 2.01 or something. So this will be approximately 0.995 or something. So if you put C equal to 1000 or something, then it will be, so if C equal to 1000 or something, so you can see, like, as you keep increasing the value of C, the precision is going to increase. So only when C equals to infinite is when you have x1 star equal to 1, and that is a true optimal value. So this is a problem with L2 penalty. When you use an L2 penalty, you have to have, like, to get 100% precision, but obviously you do not always need this thing. For example, when you are solving an engineering problem, you cannot actually measure if, for example, this x is some velocity or something, you are trying to measure velocity with some, whatever instrument you're using, say PAV, or even use some anemometer or something. Then there is a certain limitation for that instrument. Let's say the instrument can only give you up to 0.1 meter per second or something. Then what is the point in getting a, like, solving an optimization problem and giving a value that is up to 2-3 decimals precision? It might not be useful always. So you will, for practical problems, you can always have some finite value of C and still get a solution. But the only thing is, we cannot directly come up with a value of C before solving the problem. We have to start the problem, assume some value of C, again keep increasing the value of C, and see how that is affecting the final solution. And only once you are sure that the final solution is not changing within the precision of whatever your requirement is, that is the C, you are going to stop it. This is a case for an L2 penalty. Is this clear? Now let's say if you want to solve the same problem using augmented Lagrange method. So what would be my function? What would be my objective function in case of augmented Lagrange? It is going to have x, it is going to have theta, or and then you also need to have the penalty parameter c. So it will be half. Okay. x1 x2 x1 square plus x2 square plus the constraint theta times x1 minus 1 plus the penalty is convex penalty is x1 minus 1 whole square. This is what my augmented Lagrange function is. So here again, these functions again are all analytical functions. So I'm not iterating it every time. So I can directly get the value of optimal in terms of it. So I'm not writing ck c1 c2 c3. Like that is something that you can do directly. But in real problems where you have some complicated functions, you cannot always solve this directly. Now it is pretty simple. I can just put del LA with respect to x1 is x1, let's put by 2 here just so that the 2 will go off. X1 plus theta plus c times x1 minus 1 equal to 0. And then I can also solve x2, which will give me x2 equal to 0. So this is clear. This is something we got previously. What is the value of c from here? Or what is the value of x1 from here? X1 is c minus theta by c plus 1, right? Now you can see here, again, this will also change with respect to c and theta, but I do not know the value of theta. How will I find the value of theta? So how do I get the value of theta here? Or you can also, let's say if you just go with the previous thing, we know that as c tends to infinity, as the penalty becomes infinity, then it should recover the original problem. So if I do that, so if I put c tends to infinite, x1, what will that give me? C tends to infinite, 1 minus theta by c by 1 plus 1 by c, and this will again give me x1 star that is equal to 1, which is the same solution that we got in L2, but we do not actually go till c equals to infinity. All we have to do is say I can rewrite this equation something like x1 equals to c plus 1 minus theta plus 1. So let's say I write something like this. So this will give me 1 minus 1 plus theta by 1 plus c, right? Now I can choose if theta is something that I can choose. If I choose theta equals to minus 1, then this will directly give me x1 equals to 1, right? And that will be my x1 star. And it doesn't depend on c. I can choose c to be any value. Let's put c equal to 1, c equal to 2, any value. I can choose any value of c, and that will satisfy this as long as c not equal to minus 1. As long as c is some final, like the original constraint itself says that c should be greater than or equal to 0. So let's so that is inherently satisfied. So any finite value of c, c greater than 0 or c greater than minus 1, whatever it is, if I choose take a finite value of this, because theta equal to minus 1, this term will go to 0 and x1 will always be 1. So now you can see the benefit of the Lagrange method. So in L2 penalty, the only way that I can get 100% precision, like I'll always lose the precision as long as I take a finite value of c. So that loss of precision is not encountered in case of an augmented Lagrange method. So I can choose any c and still get the 100% precision. I can always get 1 exactly. This is the main advantage we are getting. But then how did I know that I have to choose theta equal to -1? So this is where the next trick comes. We know that this theta can be determined from the original theta star. So what is my original theta star? If I take the original problem, this is my Lagrange. Up until here, this is my Lagrange. So for that Lagrange, how will I determine theta? So you don't have this penalty term. So you can directly see if I take the Lagrange function without the penalty parameter. So my Lagrange function will be something like this. How do I solve it? 1 is x1 equal to 1. This is h of x equal to 0. This is how we solve the KKT conditions. So x1 equal to 1 we know, and we have del L del x1 is x1 plus theta equal to 0. Since we know x1 equal to 1, this implies theta star equal to -1 because x1 star equal to 1. And then we also know the second equation del L del x2 is x2 equal to 0, which gives me x2 star equals to 0. So all we are trying to do is make this theta equal to this Lagrange parameter. Once the theta becomes equal to Lagrange parameter, then you do not have to have an infinite value of c to recover the original solution without any loss of precision. This is clear? But in the okay, here it is very simple to get the value of theta, but usually you might not actually directly get the value of theta. Then you have to iterate. You have to start with an initial guess, and then you have to keep doing that the iteration step that we have told before. Theta k plus 1 is theta k plus your whatever penalty value you're taking times x1 minus 1. You have to keep iterating it, and then only you'll get the solution. But here it is very simple and straightforward, so I can solve it with hand. Okay, this is clear. Okay, now we'll solve some problems on, say, the cutting plane method. So I want to minimize this function x1 plus x2. This is my objective function f of x, and subjected to this particular constraint h of x. And I want to linearize this problem. Suggest anything, any linearization that you can do for this. So if I put it geometrically, so what I'm trying to do is my objective function is already linear, so there is nothing to do with the objective function. It's only the constraint that I have to linearize. So this is my constraint. How do I linearize the constraint? Say if I want to use it for cutting plane method, I have to find an enclosing polyhedron. I have to make some hyperplanes and then enclose this entire S properly. I can do it in several ways. One way is something like this. So you can just put something like this. This is one way, but that is not the only way. You can always do something else. You can always do something like this. There could be infinite ways of how to linearize this. Doesn't matter. But the point that I would like to highlight is if you, for example, if you take the first line, the first one, these particular lines, the equations will be something like x1 equal to plus or minus 1 and x2 equal to plus or minus 1. These are my equations. This is my x1 and say this is my x2. These are the equations that how I have linearized it. So original problem is s given by x1 square plus x2 square equal to 1. But now the new problem is these equations, which if I write it in the matrix form, so it will be something like, let's say for all of them it is 1 1 1 1. So x1 0. So this is my p. So I can write it in the form ax equal to p. Now it is a ax equal to b and minimize c transpose x. So it is a linear programming problem. So any of the linear programming method can actually be used to solve this. This is one way of linearization. There could be 100 different ways. Is this clear? Something like this. Ax equal to b. No, it should be of the form ax equal to b. This cannot be written in ax equal to b, right? So you have to give some values of a and b such that I can write it as ax equal to b. and it should still satisfy this thing, but obviously it won't be exactly equal to this one, but at least some points it will satisfy. It's just an approximation. Now we take the same problem and then let's say you want to solve it. How do I solve it? Let's not do the complete solution, but let's say I started with something. This is my initial guess. So these points are say 1, 1, 1, minus 1. This is my minus 1, minus 1. And this is my minus 1, comma 1. These are my 4 points. So which of these 4 points is the optimal solution? So let's put some names for them. Which of these ABCD is the optimal solution for this particular problem? So this is the original problem. I linearized it like this. So what is the optimal solution now? Yeah, it is out of the geometry. All 4 are out of the geometry. But now my problem is for this geometry, for this particular square is my domain. Like that is what we are doing in cutting plane method. So we take the original problem, but then we approximate it with a different domain. So now I've approximated with this domain ABCD. And for the domain ABCD, if I want to minimize x1 plus x2, what is the solution? With ABCD as domain, what is the solution? So where will the minimum occur? I'm trying to minimize x1 plus x2. So if you calculate x1 plus x2, where is it coming out to be minimum? Yeah, so if here the objective is how much? The point is 1, comma 1. So the objective will be, yeah, so the objective is x1 plus x2. So it will be, so if you do the same thing for all of them, where is the minimum happening? Hmm. 0. So the minimum is at, what about the third quadrant? Yeah, so the minimum is happening at D, right? Minus 2, minus 2 is the minimum of what? So I'm having, this is my minimum. But now, just as I said before, this minimum is not lying inside the original domain. Like I want it to be in the original domain, in this one, on this circle, but it is not lying on the circle. I know that circle is a convex set. Now I want to draw a separating hyperplane. So how will I do that? So this is my point. This is my curve, whatever it is. Now I have to draw a separating hyperplane. Some hyperplane I have to draw something like this. If I draw a hyperplane, then again now my new domain will be these lines. I'll use different color or different thickness or something. So then my new hyperplane will be something like this. Now in this new domain, now I have 2 more new points. Again, I'll calculate my objective function there and see which of them is minimum. And then again, with, if for example this is the new point, then I'll draw again a new hyperplane. If this is the point, then again I keep doing this till I'll reach the final, till I'll reach a point that is lying on this circle, which I'll eventually reach anyways. But now the question is, how will I draw this separating hyperplane? Like how will I proceed mathematically? So I have this function, the original function. Let's say that is my h of x as x1 square plus minus 1. So I want to find, let's say this is, okay, let's say this is x naught. I have to find an x1. I will approximate it something like this. So h of x1, if you take a linear approximation, it will be h of x naught plus grad h of x times x1 minus x0. Can do something like this. So this is anyway not satisfied. This particular thing is not satisfied. So I'm hoping that this will be equal to 0. Okay. This is very similar to how you solve your Newton method. So at x0, this is my x0. It is anyway not equal to 0. I have to find an x1 such that h of x will be 0. So all I'm trying to do is take a first order approximation, find a nearby point x1 such that this first order approximation equal to 0. Obviously, that particular whatever approximation you do, it is not going to lie on h of x because this is just the first order approximation. We have higher order terms also, which I'm not considering. But let's say if we do this, so what will this equation give me? What is x naught? X naught is -1 -1. So h of x naught is how much? If I substitute -1 -1 here, so it will be 1 plus 1 minus 1. That equals to 1. What is gradient of h of x? Yeah, it will be a vector 2x1 2x2. So if I substitute this particular point in that, it will be -2 -2, right? Now if I substitute all these values into this original equation, so h of x1 will be equals to, let's say this is equal to 0, and I'm trying to find this x1. So h of x0 is 1 plus gradient of this is -2 -2 times x1 minus x0 is sum x1 minus of -1 is +1. And I'm equating this to 0. So if I solve this, so this will be 1 minus 2 times x1 plus 1 minus 2 times x2 plus 1 equal to 0. To solve it, so it will be 2x1 plus 2x2 equals to how much? -4 and 3, right? Is that correct? So my new x1, x2 can be something on this line. What is this line? 1 by 2 by 2 plus. So it will be something like 3 by 2 is 1.5 and 1.5 is going something like this. If I missed something here, why did it go on the other side? It should be on this side, right? But I think you got the idea. You just check the sign. Do some calculation mistakes on there. But I think that is what it is turning out to be. Now you have a point here. So with this again, you have to solve these points and see where it is meeting. So eventually you will come to a point where the minimum will happen when when both of these are satisfied. So it will be something like this. If you keep iterating, eventually you'll come to this particular line. And these are the points where you'll have minimum, right? So for example, if you do it again, then maybe this will be the minimum point. And with this point and this circle, again, you will end up somewhere here. And then you keep doing, eventually you'll have to come here. I'm not doing all the iterations, just one iteration is what we have to do so that you will understand how to proceed. Process is clear, right? Okay. Yeah, these are the questions I have for this week. So now just quickly summarize. we started out from where we left behind last week. So we said that penalty function is used to convert a constraint to unconstrained problem. And to do that, we have to put a penalty parameter and some kind of penalty function. There are two different ways. You can use an L2, which is a convex kind of thing, or you can use an absolute value, which is an L1. The challenge with using L2 penalty is if you compare it with the Lagrange method that we have before, we have a finite value of theta. In order to get a finite value of theta and h of x equal to 0, we need to have ck tends to infinite, which is always not practically possible. But in all engineering problems, we usually have certain tolerance on the values of h of x. So for some very high value of finite value of ck, you will eventually get a solution. But then that value of ck is usually very high, which you do not know beforehand. So we have to keep iterating, like we have to start with a high value and keep increasing it till we reach the desired tolerance limit of h of x. So to overcome this slightly, the next method is when you can use an L1 method. Here there is no extra h of x. So we can have a finite value of ck and still get the solution. But then the value of ck that we are going to get here is still higher. It's not, and we cannot know what the value is beforehand itself. So what we use is something called an augmented Lagrange method. So wherein the value of c can be fixed, and then we try to find the value of theta, which will be equivalent to the value of the Lagrange multiplier that we solve when we are using KKT conditions. So with this method, we can know for sure that this ck is some finite value, and it need not be very high. Like you start with some small value of ck, and you might not have to perform that many iterations to eventually reach this particular value of theta. But then the problem here, as we've seen, is you have to solve the optimization problem twice. One for the Lagrange, get the value, optimal value of x, and from there update the value of theta, and again you keep solving this optimization problem multiple times. Now, all the things are for nonlinear problems, but then the solving the optimization problem itself can actually be complex with the KKT nonlinear conditions. So one way to kind of circumvent this is a cutting plane method, where we try to linearize the problem, linearize the constraints, linearize the objective function. And once we have a linear problem, we can use any of the existing linear solvers to solve the problem and see if that solution is lying in the approximated domain. If it is not in the approximated domain, then you kind of refine the domain and see if the solution is lying in it, and you keep doing that till you reach the final solution. Obviously, the number of iterations is going to be very high in this cutting plane method, depending on the nonlinearity and where your solution lies in the problem. We cannot say beforehand whether it is good or not. But then in the LP solver that we have used, we are kind of searching over all the points, all the extreme points, which is not always optimal. So then comes the next point, interior point method, wherein again we are solving both for x and lambda, but then instead of solving them one after the other sequentially, which is giving us a lot of iterations, we are again what we are doing is solving for both of them simultaneously. But again, then we end up with having a problem with the complementary slackness condition, which introduces a nonlinearity. And in order to solve for the nonlinearity, we came up with this term UK, which will kind of deviate us. Instead of making these oscillations, it will kind of direct us towards the final solution. Again, previously we were doing the optimization, we were doing iterations to find the value of lambda, and the same thing we are going to do here, but then we are doing that inside the Newton's update, where in the Newton's update we know the Jacobian value. So this is just again a system of linear equations. So solving the system of linear equations is again we have many of the linear solvers that are directly available, just a matrix inversion, or you can use any of the decomposition methods to solve this set of linear equations. So it is it will be faster than what instead of solving sequentially. And this again, you can also use the cutting plane method along with this interior point method. So wherein you have the original nonlinear problem, you first convert it into a linear problem and then you can do it, or else you can also take the original nonlinear problem and then you can also solve it directly, because this particular the way we are trying to solve is solve for this f of x, and solving this we are using Newton method, which is a nonlinear solver originally. So instead of this, I can have a nonlinear equation here, and then but then the only problem is this Jacobian will be a little more complex then, that you have to solve for. If you can find the analytical function, you can find the analytical derivative. Otherwise, you have to use something that we discussed last week, something like BFGS, where you use an approximate derivatives to get this Jacobian, and then use that Newton update. Yeah, that's it for this week. Have any other questions that you want to discuss? All the optimization methods we have is so you have been solving OR problems, right? You have been through gate, right? I think you have been through gate. Oh, you are not through yet. Okay. So, if you have seen any of the operation problems or the network analysis problems that we discussed previously, like you want to maximize inventory or queuing or any of the problems we discussed before, in all those problems you can use these methods. Say you want to go from some point A to point B, and then you want to determine the optimal route so that your total timing is minimized or something like that. Or let's say from a mechanical point of view, you can have some problems where, so for example, let's say you have a heat exchanger. The main thing in a heat exchanger is you have to increase your net heat transfer without compromising on the work requirements, right? Like without compromising on the pumping power requirement. So that is the main thing in a heat exchanger design. So you formulate your optimization function in terms of whatever cost function that you have, depending on the amount of material you have and all of that. And then your constraints will be, say, for example, if you have a shell and tube exchanger, your constraint could be something like the number of tubes you have to use inside it, the diameter of the shell, and all these things will be your constraints. Those constraints you can linearize because the original constraints are non-linear. You have to linearize them. And then another challenge that comes is the number of tubes is an integer. It cannot be any random value. Like it cannot be 1.5, 1.2, 1.8 kind of stuff. So there again, you have to split your domain. So for example, you have this is your domain and this is your integer variable. Then you cannot take anything in between. So only this value and only these values are useful. So this is also something where you use the cutting plane method. They have a different name for it, but then eventually the point is the same. So cutting plane will ensure that you always cut only at these points. So that way you'll ensure that you only get the integer solutions. But then again, the idea is the same. You start with something and then you decide how far to go. If I started at this and if it is not equal to 0, how do I approximate it? What will be my new boundary? Should I keep it here or should I keep it here or should I keep it here? That is something that is what we are doing in your cutting plane method, right? We are determining the next optimal cut where we have to do. There are a lot of other problems, but eventually these are the most general class of things. We are not discussing any problems here. Maybe in the last week I'll take some problems and maybe we'll solve, or instead of solving, we don't have that much time. I'll show you the solutions so that you can understand how these are related in the last week, next Sunday or so. Yeah, since it is more on the theoretical and your assignments are theoretical, I'm not actually taking any numerical problems. Then maybe in the last week we'll take numerical problems. So if you are appearing for the exam as well, so only MCQs. No, all of them will be MCQs. They're similar to your assignment questions. Whatever assignment questions you are going to have, they are going to be of the same type. I'm not saying they're the exact same questions, but they will be similar questions. Okay. Any other question? Yeah, some problems. Yeah, I have to have something. Sometimes it happens. I do not have any because I'm not the one who will be on that part. It will be from a superintendent. But the only thing that I can say for sure is if you have solved all the assignment problems, you are going to have most of the questions from your assignments. Most of it, I don't know how much percentage it is, but maybe some 60 percentage or something has to be exactly the same questions, and you'll have some new questions as well. But most, if you are thorough with your assignment questions, then the exam is going to be easy. That's the only thing I can say. I don't know beyond that. No. Fine. Any other thing? Okay. If you have no other questions, then I think we can end the session for today. Thank you for joining.